Astronomers have found a planet that looks far too heavy for its size. GJ 523b is only about 2.5 times wider than Earth, yet it contains roughly 23.5 times Earth's mass. Its average density is around 7.8 grams per cubic centimeter, making it denser than Earth despite being much larger. Even stranger, the planet is only about 170 million years old and appears to orbit almost sideways around its star. Researchers argue that GJ 523b belongs to a rare class they call mega-Earths, planets large enough to approach the size of sub-Neptunes, but dense enough to contain surprisingly little gas. That combination creates a problem. Standard planet formation models usually expect a world this massive to capture a thick envelope of hydrogen and helium while the system is young. GJ 523b appears to have avoided that fate, lost most of its atmosphere extremely quickly, or formed through a much more violent pathway. The planet orbits a K-type dwarf star called GJ 523, about 87 light-years from Earth. NASA's TESS mission first detected the planet as it repeatedly crossed in front of its star, causing a small dip in brightness. Those transits revealed its radius, but radius alone cannot tell astronomers what a planet is made of. A large world could be rocky, water-rich, or surrounded by an enormous gas envelope. To measure the mass, the team used the NEID spectrograph on the WYN 3.5-meter telescope in Arizona. Instead of watching the planet cross the star, NEID measured the star's tiny motion toward and away from Earth as the planet's gravity pulled on it. Combining those radial velocity measurements with TESS observations gave the researchers a mass of 23.5 Earths and a radius of about 2.55 Earth radii. Those two numbers reveal the real mystery. Imagine expanding Earth until its radius becomes 2.5 times larger. Its volume would increase by more than an order of magnitude. If that giant Earth retained roughly the same composition, its total mass would increase dramatically. But planets at this size do not normally behave like scaled-up rocks. Above roughly 2 Earth radii, astronomers often begin finding sub-Neptunes with thick atmospheres that lower their overall density. GJ 523b breaks that pattern. With a density around 7.8 grams per cubic centimeter, it is denser than Earth, which averages about 5.5. The results suggest that most of GJ 523b's mass is concentrated in heavy material rather than a deep hydrogen-helium envelope. The researchers estimate that the atmosphere, if one survives at all, must represent a surprisingly small fraction of the planet's total mass. That is particularly strange because the planet is so young. The team studied the rotation of GJ 523 and several stars moving through space with it. Stars generally slow their rotation as they age, allowing astronomers to estimate age using a method called gyrochronology. Their analysis suggests the system is about 169 million years old, with substantial uncertainty, but still dramatically younger than our 4.6 billion-year-old solar system. At that age, a massive planet would normally still carry clear evidence of its formation environment. If GJ 5023b formed beyond the snow line, where volatile materials and gas were abundant, it may have accumulated a substantial envelope before migrating inward. If it formed close to the star, building more than 20 Earth masses of dense material in such a small region would itself be difficult. One possible explanation is atmospheric loss. GJ 523b circles its star every 17.75 days at a distance of roughly 0.123 astronomical units. Its estimated equilibrium temperature is about 538 Kelvin, or approximately 265 degrees Celsius, assuming it reflects no incoming light. Young stars can also emit intense high-energy radiation capable of heating planetary atmospheres and driving gas into space. But the planet's enormous gravity works against that process. A world containing more than 20 Earth masses should hold onto gas much more effectively than a small super-Earth. Removing a thick primordial atmosphere from such a massive planet in less than a few 100 million years could require unusually intense irradiation or a dramatic event. That brings us to the planet's orbit. The researchers estimated that the star's rotation axis is tilted only about 17.6 degrees relative to our line of sight. Because GJ 5023b transits the star, its orbital plane must be viewed almost edge-on. Put those two geometries together, and the planet's orbit appears strongly misaligned with the star's equator. The team calculates a minimum orbital obliquity of roughly 71 degrees. In simple terms, GJ 523b may travel around its star on something close to a polar orbit. Our solar system is comparatively orderly. Most planets orbit near the same plane and in roughly the same direction as the Sun rotates. That structure preserves the geometry of the disk from which the planets formed. Strong orbital misalignment usually suggests that something disrupted the system later. A massive neighboring planet could have gravitationally tilted GJ 523b. A close stellar encounter early in the system's history might have disturbed the orbit. The planet could also have experienced high eccentricity migration, where gravitational interactions first stretched its orbit into an extreme ellipse before tides gradually pulled it inward and circularized it. Another possibility is a giant collision. Imagine two large young planets forming in nearby orbits. If their paths became unstable, a collision could remove much of their low-density gas, while combining their heavy interiors. The surviving planet would become unusually massive, unusually dense, and possibly end up on a highly tilted orbit. That scenario fits several pieces of the puzzle at once. It could help explain the high density, the lack of a large gas envelope, and the strange orbital geometry. But the researchers emphasize that there is not yet enough evidence to determine exactly how GJ 523b formed. This is why the planet is scientifically valuable. Instead of fitting neatly into one familiar category, it sits near the boundary between rocky super-Earths and gas-rich sub-Neptunes. The researchers propose an observational definition for mega-Earths, planets with radii of at least 2.1 Earth radii and densities above 5.5 grams per cubic centimeter. They identify a small population of known worlds that could belong to this class, including GJ 523b. The name is less important than the physical question. How do planets become this large without becoming gas-dominated? Planet formation models begin with dust colliding inside a disk around a young star. Tiny grains become pebbles, then planetesimals, then planetary embryos. Once a rocky core reaches several Earth masses while significant gas remains in the disk, gravity can begin capturing hydrogen and helium rapidly. A core approaching the mass of GJ 523b should therefore have been extremely effective at gathering gas. Yet today, the planet appears mostly heavy material. That could mean its atmosphere was stripped away. It could mean the planet formed after much of the gas disk had already disappeared. Or it could mean several smaller planets merged after the gas was gone. Each possibility tells a different story about how planetary systems evolve. The planet's youth makes those scenarios easier to test because less time has passed to erase evidence. Astronomers can search for additional planets that might have disturbed its orbit. More precise measurements of the star's orientation could confirm how extreme the misalignment really is. Improved mass and radius estimates would tighten the planet's internal composition. Atmospheric observations may be even more revealing. If GJ 523b retains a thin atmosphere, its chemical composition could reveal whether it once had a much deeper envelope. Heavy molecules might survive after lighter hydrogen escaped. Alternatively, a nearly bare rocky world could show that even an enormous planet can lose most of its primordial gas under the right conditions. There is also a broader lesson. For years, exoplanets were often organized into simple groups: rocky Earth-like worlds, Neptune-like gas planets, and giant planets like Jupiter. Thousands of discoveries have shown that nature does not respect those clean boundaries. Some planets are larger than Earth but less dense than water. Others are close to Neptune in size but contain astonishing amounts of heavy material. Some orbit backward. Some travel near their star's poles. Some appear to have lost almost every trace of the atmosphere they were expected to possess. GJ 523b combines several of those extremes in one young system. It is more than 23 times Earth's mass, only about 2.5 times Earth's radius, hotter than an oven, and probably moving around its star on a dramatically tilted orbit. The planet does not yet tell astronomers exactly what happened. That is what makes it interesting. Something produced a world massive enough to become a sub-Neptune, dense enough to resemble an enormous rocky planet, and dynamically disturbed enough to orbit almost over its star's poles. At only around 170 million years old, GJ 523b may be showing us the aftermath, while the evidence is still fresh.